Next.
Hello. Check. My testing.
Jagiellonian. The J is pronounced as I. Polish is a really difficult language. They have words with 4 or 5 consonants back to back. Yes. Yeah.
Hi, Roji. Are we waiting for someone?
Jay, yeah, we are waiting for the other faculties to come, so they are all in the canteen.
I see. Okay.
Please wait 2-3 minutes, we'll start.
Okay. Just check.
Okay. Yes, yes. Aim so to. Yeah, yes. Yeah, yeah. Okay, we are happy to have Samapan Badri from ITP Jagiellon University. So he'll be talking about formulation of relativistic hydrodynamics. Okay.
First of all, I'd like to thank you for giving me the opportunity to present these works here at IMSC. So I was at IMSC around 6 years ago. So it's nice to be back here. So I'll be talking about the formulation of relativistic hydrodynamics. And so hydrodynamics is a theory that has a wide range of applicability. And some of its applications include studying the evolution of hot QCD matter known as QGP in heavy ion collision experiments. So my research so far has been focused on that application that I have used relativistic hydrodynamics to describe the matter produced in heavy ion collisions on experiments. But there are other applications as well, like some astrophysical studies and gravitational theories also use hydrodynamics. And more recently, there are some condensed matter physics theories where they have been using hydrodynamics. And more surprisingly, to my surprise, there is a recent study where they have been using hydro in biophysics as well, not relativistic, but hydrodynamics. So one has to wonder why hydrodynamics can explain systems of such wide range of variety. So there must be some underlying fundamental principle behind it, and to understand that, we have to uh, consider the relevant scales involved in hydrodynamics. So if we consider our system size to be some L, then one of the first things is that the variation of the macroscopic fields like temperature, chemical potential, or fluid velocity, it is assumed that these variations are rather slow as compared to the system size. So the variation can be significant over the range of the system size or maybe smaller, but not too small. But the more important parameter scaling is this one, the interaction length. So this is something like the mean free path of the collisions in the system. And this has to be much, much smaller than the system size as well as the variation length of the system, microscopic variables. So this kind of scale hierarchy, if that is followed, then hydrodynamics can be applied. And in nature, this kind of hierarchy is followed in many systems. That's why hydrodynamics is applicable. Now, following from this hierarchy, one can formulate hydrodynamics in a order by order gradient expansion. So that is what, so these gradients depend on this scale relation. I will explain that in more detail later. So consider some macroscopic density as a rho and its corresponding current J. So they will follow this kind of equation, which is nothing but continuity equation. So this is the general kind of structure for a hydrodynamic equation. And both this J and rho can be expressed in as a gradient series of some underlying macroscopic fields. These phi's can be some temperature, fluid velocity, or chemical potential. So these are called the constitutive relations of the system. And if we truncate our theory to such that there is no gradients involved, then I have only this term, and this theory is the perfect hydrodynamics. For
Hi,
first order,
one question. So regarding this truncation, as you said, whenever you are doing, for example, also in the Vlasov-Moisov equation, this truncation depends on the system, right? It depends particularly on the system, because if you add this pressure term or the gradient of the pressure term, you really don't know which one will blow up at what point. So does it really guarantee that if you truncate, that is the that is a conservative estimate, or the other terms, other higher order derivative terms will be significant at any stages?
Yes, yes. So, in principle, one should consider all terms, but that is kind of impossible to compute the system. So, we start with some zeroth order truncation, which is perfect hydrodynamics, and then we go on correcting first order and second order. But for this kind of series to be valid, one has to assume that the gradients are smaller. So that is what this scale says, that if my gradients are much smaller, then this kind of expansion is valid, and maybe my theories can explain with a finite number of truncations. So there are theories where first order truncation is not good enough, but we have to consider second order truncation and maybe even third order truncations. So it is like depending on this particular system, as you said, that which up to what degree of accuracy I have to work on. So,
And
that,
does it add the number of parameter as you go on adding different
yes. So,
gradients? It increases the parameters, right? So the system becomes less deterministic.
can you repeat the last part?
Yeah, I'm just saying that if you include, for example, for pressure term, for the gradient of pressure term, it comes with extra parameters, right?
Yes,
So
yes,
that makes the system, your analysis less deterministic.
yes,
Actually, one needs to solve the full Boltzmann equations and things like that, right?
yes.
So I understand that because if the phase space behavior, it becomes too complex and you cannot solve it for everything. So that is why you are resorting to the fluid dynamics. But here I mean, this is my concern, that you, at some point of time you may encounter cell crossing singularities and things. And in order to avoid that, if you keep on adding terms to certain extent or to certain scales, your theory will be valid, but it will also add these parameters and make the theory less deterministic. So this is my whole concern as such.
Yes,
Neeraj, can I add something? So, the
Sure.
Boltzmann approximation is not valid for systems which do not have quasi-particle like picture. So, Boltzmann approximation is anyway not valid for our system like UCD or heavy ion collisions. One may derive some hydrodynamics from Boltzmann equation or kinetic theory like picture, but the hydrodynamic picture is very general. It is for the long wavelength modes of the system. Now, depending on the anisotropy of your system, you have to truncate how many terms you have to take. But otherwise, it's much better than the Boltzmann equation, because the Boltzmann equation is only valid in a system where you have valid quasi-particles, which is not true for QCD at finite temperatures.
yeah, that's why we
Okay.
use a Boltzmann equation and take moments and then formulate hydrodynamics from it, because the evolution we want is should follow the hydrodynamic evolution equations.
Okay. Okay.
Yes, I mean,
In doing so, do you ever encounter this cell crossing singularity?
Maybe you can answer Dheeraj's question first and then come back to
what singularity?
Dheeraj, can you
Cell
repeat what
crossing.
you were saying?
Yeah, I was saying that do you ever encounter cell crossing singularity? Because I assume that when you are solving these equations, you are doing it in a grid, right? In a like a 3D
No,
grid.
no. So,
Dheeraj,
so
this is only slide 3. Can he please go on so we can understand what he's done before you ask such detailed questions? I find it really puzzling.
Okay.
Carry on. Proceed.
you were asking.
No, just they satisfy some equation.
Yes. So these densities, they have some equation of state they satisfy, and that we can, because we have this kind of constitutive relation, we can also express these relations in terms of the phi's as well. Okay, so this is a. So where I stopped is that this kind of scaling is important for such gradient expansion, and heavy ion collision is a system where this it pushes the limits of hydrodynamics, because the system size in heavy ion collision is really small, and there are certain situations where one cannot forcefully say that this kind of hierarchy is maintained. So that is why studying hydrodynamics in the context of heavy ion collision is interesting physics for us. So this is a description about heavy ion collision. So we know that this fluid being produced, QGP, it has a very small but finite viscosity, and that's why relativistic dissipative hydrodynamics is required. So this is a schematic diagram of heavy ion collision. Before the collision, these are the incoming heavy ions, heavy nuclei, and this is impact parameter. So if B is 0, then what I call is a central collision or head-on collision. But when B is finite, I have a non-central collision. And in this non-central collision, there are some nucleons who would collide with each other and form this medium of interest called the participants. And the nucleons are participants. And there are some nucleons which will not collide and move away from the collision region. These are called the spectator particles. Now, the spectator particles have consist of protons, and that's why they are charged. And because they have such large velocities, they can produce large magnetic field as well. So in non-central collision, when we have finite impact parameter, there can be large angular momentum, large magnetic field. And as an interplay of these two, the system can become also spin polarized. So we want to construct a formulation of hydrodynamics that can describe all these aspects, that rotation of the fluid, magnetic field, and also spin polarization. So for this, we start from the basic idea that hydrodynamics is built on the idea of conservation laws. So for the starting point, if I consider the traditional theory where non-rotating charged fluid is there, these are the relevant conservation laws: the particle force current and energy momentum tensor. Now, at our disposal, we have the tensor degrees of freedom, that is fluid velocity, fluid flow velocity, and the metric tensor. Using these, we can tensor decompose these to conserve current in this manner. This is the most general tensor decomposition, provided the energy momentum tensor is symmetric. So this is the assumption, and we proceed with this. And usually in hydrodynamics, one works with the Landau frame or Eckart frame of the fluid velocity, but this is without any particular choice of frame. This is a general decomposition. So in perfect hydrodynamics, the system of equation is closed, provided we give the equation of state. But when we have to consider dissipation as well, then the number of unknowns are much more, and we need some underlying microscopic theory to describe the extra degrees of freedom. For my research work, I have mostly worked with relativistic kinetic theory. So
description. What would be the particle? You say net particle for current. What is the particle there?
So I mean, these are not particularly particle, but the net charge of the system. Like it can be the net baryon number or net strangeness or some degrees of freedom like that. So here I mean actually the particle minus antiparticle number as well.
I have a short question. This is Ravindran. Can I ask you? You mentioned about this energy momentum tensor and net particle flow current. Maybe I'm wrong. There are some works by Siraj Minwala on modifying, this thermodynamic equations or hydrodynamic equations, which Landau and Lipschitz, sort of. Are you aware of that actually?
No, I mean I have followed some works by Shantanu Bhattacharya with Siraj
Yeah,
Minwala. Yeah.
There is no relevance in your analysis actually.
No, they are highly relevant. Like those are some fundamental works. So they give us the idea of, for example, how many transport coefficients are there. I mean, and what are the possible tensor structures can be formulated in some particular, say, second order hydrodynamics theory. So they gave us some very fundamental ideas about the theory itself.
That's not useful for your analysis.
So
that's not used in your analysis actually.
Yeah, no, we don't use it, but we get some idea from this particular.
Okay.
Second order hydrodynamics, dissipative. So those terms should be there in this.
Yeah, the terms are there. So
Yeah.
I mean, they formulate it with some fluid gravity.
They got it from some other way, but those terms should be there in this equation of hydrodynamics.
Yeah, I mean, there are, but sometimes when I formulate the theory from kinetic theory, there are some type of tensor structures that are missing and in those theories. So
But that is, you know, why the reason is, why is it missing in that?
I mean, for say there is one particular term in second order theory, like there is a coupling between vorticity and vorticity that is missing here because the particular theory that we use a local collision, considered local collision. That's why these kind of terms are missing. But there are some theories with kinetic theory as well where they have considered non-local collisions. So maybe if we construct second order theory from there, then those terms should appear.
Why do you expect, because those theories, the underlying principle there is to use quasi-particle less using ADS-CFT correspondence they found out. And here you are assuming it's a quasi-particle like picture, and of course now you always take the long wavelength limit of it, right? When you do it from kinetic theory. So fundamentally the starting points are different. Does it make any issues?
Yes, as I said, the underlying microscopic theories are different, but the macroscopic picture is similar. So, I mean, the available tensor degrees of freedom I can always construct, but whether it exists in the particular microscopic theory I am considering or not, that's that I have to look into the particular theory itself. So,
okay.
Was any question? Okay. So now coming to the description of kinetic theory, the central object is the phase space distribution function, and we can take different moments of the phase space distribution to obtain these conserved currents. And in general, my system is in out of equilibrium state, and that's why I can decompose this into equilibrium part, the FAQ, and the non-equilibrium part. In the literature, we often use this phi notation as well. Here, this phi tilde is defined here, and A is for different statistics. So, in the equilibrium part would generally look something like this. This is a known structure, but G can be different for different systems. For example, in this case of non-rotating charged systems, the G would look something like this. Here, alpha n are the Lagrange multiplier associated with the particular conservation law, and phi n's are something called collisional invariant. I will explain that in the next slide. So these are the one possible structure, but there can be many other systems as well. So we know this equilibrium part, and now we have to determine the delta F, the out of equilibrium part as well. For this, we have to consider the Boltzmann equation. So in the Boltzmann equation, the first term on the left hand side is saying how the distribution evolves in space time. The second term is the evolution under the influence of some external force, and on the right hand side we have the most important entity, the collision kernel. So the collision kernel involves all the information about the microscopic collisions or interaction processes. So in general, collision kernel can be a very complicated quantity. For 2-to-2 collisions, the general structure would look something like this, where W is the transition amplitude. But so in this Boltzmann equation itself is an integral differential equation. And moreover, this collision kernel itself can be a nonlinear quantity. So to make our life easier, we often linearize this collision kernel, and it looks something like this after linearization. So now there is this particular combination of these phi's highlighted in red. So when for those particular phi values for which this combination vanishes, they are called collisional invariants. Now, the collisional invariants are important because they are those quantities that remain conserved during microscopic collisions, and also they correspond to macroscopic conservation laws as well. So there is one macroscopic conservation law corresponding to each collisional invariance. So if I want to have a number conservation, the collisional invariant will be just one. For energy conservation, it is particle energy, and so similarly for linear momentum. So ideally, I would like a linear collision kernel to follow these properties. Now, in addition to these properties, the linearized collision kernel also satisfies this property, which together with this allows us to ensure that conservation laws hold. For example, if I take the zeroth moment of the Boltzmann equation. So on the right hand side, I will encounter this term, and I can use this property to turn this term into this one, and which is now 0. So that means my number is conserved. Similarly, I can show that for the energy momentum conservation as well.
How do you extract L hat? In the previous slide you had.
Yeah. So this is I substitute this F like this. So F
Okay.
is substituted here, and then I keep only the linear terms there.
Nice.
Yeah. And we have to also use
after integrating, is it?
No. This form is without integration. So we have to consider this.
So L hat will have some integrals in it, or what?
Yes. So this is integrated over these momentums.
So L hat will have some integrations in it.
Yes.
Okay.
Defining M hat slightly equals right-hand side, right?
Yes. Okay. So there is some detailed balance conditions also involved here to get this form. Okay, so now I will come into the works that I have done after this introduction. So the first starting point for collision kernel is Anderson-Whitting RT. This is the most okay. So we have to assume that the variations are not too large. I mean, delta F is much smaller than the distribution itself. Yes, close to equilibrium. Okay, so the first starting point should be the RTA because it has been widely used in the literature. So what RTA says is that the natural tendency of a system, out of equilibrium system, is to move towards equilibrium through because of the collisions with characteristic time scale tau r, which is called the relaxation time. Now this relaxation time involves all the information about the microscopic collision, the interaction, cross section, momentum of the particle, everything. But so in general, the relaxation time should depend on the particle's energy or momentum itself. But when we do this, make this relaxation time energy dependent, then the relaxation RTA cannot ensure the conservation laws anymore. So like the energy momentum conservation, number conservation, those
all of them.
Yes, the moment we make it energy dependent, so it can be seen very easily that if my relaxation time is not energy dependent and I take the first 0th moment, then it will come out of the integrals. And what I'm left with is this u mu delta n mu, and that is just 0. Similarly, for energy momentum density, it will be u mu delta T mu nu, which is nothing but the Landau frame condition. So I can get the conservation from there. But then when it becomes energy dependent, I cannot take it out of momentum integral, and this is a problem. So this paper was the first one where they found that it is possible to modify the collision kernel itself and such that the relaxation time is energy dependent and the conservation laws are still valid. But this is a very technical paper, and we found that there is a much simpler process to explain this, and we also found some very interesting intuitive ideas about why this happens. So another thing I should also mention that because of this RTA, the construction of RTA, it is only working in the Landau frame. It cannot work in any other frame of the hydrodynamics.
So in your case, the relaxation time depends on energy.
Yes, it can depend on energy.
In the place where you want to apply it.
Yes.
And what is the reason for it? In which situation will it depend on energy?
So, I mean, in general, it should because the relaxation time involves the information about the collision cross section.
Okay.
That itself says that it should have some energy dependence. But the theory we have been working on so far, we could not do this. So this is on very recently that we have been able to work with momentum dependent relaxation time. So to understand how our framework works, we have to distinguish between two ideas, the thermodynamic frames and hydrodynamic frames. So the terminology frame is a misnomer. So this does not have anything to do with frames or fluids velocity or those things. This is just the terminology used in literature and we are stuck with it. So in general, when you're working in the out of equilibrium system, these variables u, mu, t, mu, they're not well defined because it's an out of equilibrium system. How can we define the temperature? Temperature is only defined in the equilibrium only. So these itself are not the true temperature or chemical potential of the system. Now, when we are defining the equilibrium distribution function using these variables only, then this is also not a real equilibrium of the system. Rather, this is an artificial equilibrium state, we call it. So this is the main problem of the RT, that when we are writing like this, that we assume that system moves towards this F equilibrium, which should be the local equilibrium of the system. But in fact, this is not the true local equilibrium. So there is some thing missing here. So that's what we wanted to cure. And so we define these starred quantities, which we call the true thermodynamic equilibrium. And that's why we dub this term thermodynamic frames, thermodynamic variables, and these hydrodynamic variables. So, and they are related like this. And our proposal of the new collision kernel, we call it extended RTA. And it looks like this. It does nothing but replace the artificial local equilibrium by the true equilibrium of the system. And it has the exact same form because it is the true equilibrium distribution. So this is how it looks like. And we can also relate it to this artificial equilibrium through this. Now, this linearized collision kernel would now look like this with the help of these equations. So now we note that if we forget this phi star here and consider only this term, this is what the RTA was. So what this phi star and this new thing is doing is it is subtracting something from the RTA. So what is it? Later we found that this phi star is nothing but the homogeneous part of the Boltzmann equation. So Boltzmann equation is an inhomogeneous differential equation. So it will have some homogeneous part of the solution and the particular integral. So this is the homogeneous part of the solution that gets subtracted, and this phi star contains this delta u, delta t, delta mu, which is crucial to define the particular frame and matching conditions of the system. So once we subtract this phi star from the solution, then we become independent of the choice of frame and matching condition. That's why when we are working with ERT, we are not bounded with the fact that we have to work only in the Landau frame or Eckart frame. We can consider any general frame. So
means that you have removed the collisional kernel.
yes.
So that part is universal. That doesn't know anything about what system you are studying,
Yes.
right? Because the other part is just phase-space conservation. So what is your statement now? If you remove that universal part, then you cure. So what was the statement? I didn't follow.
So the point was that this is the homogeneous part of the solution, and it is a function of these delta u, delta t, delta mu, and they define which frame I'm working with. If my delta u, if I'm working with the Landau frame, the delta u is 0. So these contain these information, and that's why when I subtract this information from the full solution, this part becomes independent of these quantities, and now I am free to choose any particular frame and matching conditions. Okay. So if I truncate my theory up to first order, then the phi star would look something like this. It's not important. So to actually work with some momentum dependent relaxation time, we have to do some parametrization. I mean, it's not really necessary to do the parametrization to do the calculation, but at the end, if we want to do some plottings of shear viscosity and bulk viscosity, we need some particular parametrization. So in the literature, this kind of power law parametrization is widely used, and this parameter L, we will see in the next slides that how things depend on this particular L parameter.
But when you say widely used, there should be some constraint on the system that you're talking about.
So in general, the value of L is constrained between 0 and half for QCD-like system. And also recently we have found out that if I consider L equals to 1, that corresponds to lambda phi 4 theory.
And when you tell QCD-like system, it is at very high temperatures, perturbative QCD.
Yes.
And is there an understanding why is it between 0.5?
I don't know. I don't think so, because this was a paper by Guy Moore, I think. They showed that they did some calculation and showed that they had some observables, and for particular values of L, they gave this. I mean, should correspond to QCD-like theory or.
So I guess they calculated eta from perturbative QCD, and then they matched it with the kinetic.
Yeah, I think so. Yes, yes.
Dependence on X. What does that? What is that saying?
Yeah, I mean, so it can be function of temperature or chemical
X
condition.
is not
Space-time.
position, but
Yeah, I mean, it can be space-time. So it's dependent on space-time.
but dependent on space alone is possible. Is that X supposed to be space or is
No,
it?
it's space-time, 4-vector.
Okay. In which situation will you get the relaxation time dependent on space time? Not momentum, but space time.
Well, it for any system, I mean, it depends on the energy scales involved, right? So if my
No, that should be contained in that L, no?
Yeah, so in general, when I mean, before this momentum dependent relaxation time process, what one used to do is average out the momentum dependence and get a average relaxation time. So it contained the variation of the space within itself.
Okay.
Yes, there is no restriction for this particular L, but I will come to one other example as well.
Hi, I
So
just
we
missed one point. Sorry. So this, in which condition you said that this tau r xp can be, I mean, written independently of x and momenta separately, not with in this case?
so actually
Can it be written every time, or it is a kind of an approximation that you are?
No, this is always an approximation. Like in general, the relaxation time should be momentum dependent. But in earlier studies, because we did not have this kind of tool, we integrated averaged over the momentum and then obtained something that was only dependent on space time.
Okay. Okay. No, as I understand, it is still dependent on momentum, but you are able to write them of two independent functions, one dependent on the space-time and one on momentum, right?
Yes. Now this is just a parameterization. We don't know that, I mean, whether this is always hold true or not. There can be some other parameterization scheme as well. That's why I said this kind of parameterization scheme is used in the literature most widely. That's why we use it. But we know there are certain cases where this will fail.
Oh, okay. So because I was confused with the term parameterization then, because it is a functional form that is, I thought that it is kind of an assumption which you are saying that it is a parameterization, which you are referring to a parameterization. Okay, fine. I understand now.
Okay. So we use this kind of expression and did some studies on the scaling properties of the system. This was the first order. First, we studied the first order theory with this is for the bulk viscosity to shear viscosity, and we've noticed that in the large mass limit, which corresponds to the non-relativistic system, independent of what is the L value or what is the statistics of the particle, they all converge, saturate towards this value of 6. And for ultra-relativistic system, it really depends on what particular choice of statistics and what particular system we are considering. So there are some particular scaling values here that we studied, just to see that L does matter. The value of L does matter to fix which particular system I'm working with. This kinetic theory.
So what are the two curves there, blue and red?
So this is for Maxwell-Boltzmann statistics, and this is Fermi-Dirac statistics, the particles.
Okay.
Underlying
So
quasi-particle.
this is with some interaction that you have assumed, or they don't interact?
No, we do not. I mean, yeah, they interact, but it's not coming out from fundamental QFT. It's just this collision kernel that we are considering.
So what is the collision kernel you have taken for these?
This ERTA collision kernel.
Okay. But with some arbitrary parameters that
Yes.
you have taken those functional forms with arbitrary parameters and then you're making those plots.
Mhm.
Huh.
What is this mass here actually? Small m.
Yeah, but it is not.
Mass is like the particle mass of the quasi particle or particle that I'm considering. The constitutive
QC.
particles of the system.
This is for QC.
From the QCD, is it?
Yeah, I mean, we claim it the QCD, but I mean, this is any general system like so. Yeah, we can treat m as a parameter.
There is no m really. It is m by t, and that is the variable in the Boltzmann equation, right? So, or whatever equation that you have.
Sorry.
Yes.
Yeah. So, is there any difference you observe between the QCD like parameterization and?
Yeah, I mean, this scaling values differ. Like, so there is one example where Weinberg had a study on radiation interacting with the medium. They found that this value would correspond to 15. And that's what we find in the L equals to 1 case. And
It's for the early universe context, or which
Yeah.
context was it? The inflaton or scalar fields?
I don't
Because
remember.
this is corresponding to scalar field L equal to 1 case.
Yes, L equals to 1 is a scalar field. So I'm not saying that this is exactly that same system, but it is possible that by varying different L's, we can incorporate the phenomenology of different systems in the theory itself.
And why for large mass it is going to some same number?
Yeah, so large mass corresponds to the non-relativistic limit where the nothing moves practically. So in that case, my CS square would be 0. And we can also do the expansion of this zeta by eta in the large mass. And we find that irrespective of what the particular choice of L is or what this statistics is, the ratio is always 6, this value. This is mass of what? Mass of the constituent particles, whatever the medium particle is.
So this
What
is
is
not
this
a
MB
fluid.
and FD actually?
The Fermi-Dirac and Maxwell-Boltzmann statistics.
Okay.
So this is not a fluid description now?
Yeah, I mean, the evolution equation is a fluid,
Okay.
but there is an underlying microscopic theory in the system.
Okay. And that is in that collision
Yes.
kernel. And so you are actually having QCD with a certain mass.
Mhm.
And what would be the mass of which particle is it?
So no, this is not any particular particle. This is how we're studying that. Say, let's consider how these parameters vary with mass. So if I can have
Mass
a particular
mass of what? I mean, I can say if you have a constituent theory, then there is a mass of some particle in that.
Yes.
If it's a particle description of that.
Yes, but
which
what
you can then take the fluid limit off. Is it that kind of a picture or?
Yes, yes. So, but
okay.
we do not particularly mention which particle it is. So it can be some quasi particle quark like quasi particle or something like that.
Okay. Is your interest in applying it to a realistic situation, or are you studying?
No, this is eventually we want to compare with the experimental data.
And what mass will you choose when you try to compare it to experimental data? What it
So
would be the
that
mass
will depend on the particular system. So if my system is say consist of only up and down quark, then I have to work with only those masses.
Okay, it would correspond then to the up and down quark masses.
Yes, yes.
I see. Okay.
Quasi-particle mass.
Yeah, I mean, we say it up and down quark, but honestly, this is just quasi-particle picture. That is true.
And in a thermal system, it gets modified very strongly, right?
Yes, I mean, then later we
Each
did.
quarks and gluons have thermal correction.
Yes, yes. So later
these are quite large.
Yes, later we do some works where we also incorporate those variation of masses with temperature as well.
And this is done in which approximation? Are you using HTL or something? Or?
No,
because the dispersion relation is different if you have different effective theories of high temperature.
No, we use the equation of state from lattice QCD.
But then you will have problems with thermodynamic consistency.
Yes, we do correct
Okay.
that with the back pressure.
We will talk about.
Yes. No, this is the hydro variable because we are doing hydrodynamics itself. So this is out of equilibrium temperature. That's why whenever we're doing this expansion of the true equilibrium in terms of those hydro variables. So, yeah.
Right? Now you're distinguishing Maxwell and Fermi-Dirac, so why not Bose-Einstein?
Yes, so Bose-Einstein has this problem of convergence of integrals. We did try to do that, and there are some plots, but after certain values of this L, they don't work. I mean, we cannot ensure the integrals converge. That's why.
What else? Okay, cool. Just to be indicated.
Yeah, so I mean,
What else we can
below
so
L
this
equal,
one.
yeah, below L equals to 2, we cannot ensure the convergence of the integrals.
The reason I'm asking is that if you are distinguishing Maxwell with Fermi-Dirac, if it is higher of temperature, you can't.
Yes.
This matters only at lower temperature, the distinction.
And that's why these are all
And
convergent.
your theory doesn't work for boson, but it's also measured with that.
Yes.
This approximation doesn't work for bosons. That's why I mentioned that. Because even fermions become bosons.
Yeah.
The typical thing would be a boson. All your currents are bosonic currents. They're not fermion. Because they're all difference of charges, and that's two fermions, they form a boson.
Okay.
Most of the distributions should to boson.
Yeah, but we can't solve the integrals itself, so that's. I mean, we suspect that it is because of in the low momentum region, this Bose-Einstein condensation.
It will condensate, but there in the unitary limit, what will be the relaxation time? Because in unitary gas, they have some relations.
Okay.
So I don't know whether it is relevant here, but people study in cold atoms.
Okay.
It's at some temperature. Takes you away from that.
Yeah, but so we did not do that part. So now we can go to second order theory. To start with, we only consider massless and chargeless systems, where the only relevant dissipation is the shear viscous pressure, and this is what the equation of evolution equation of the shear viscous pressure looks like. So now this tau pi is the relaxation of the shear mode, only shear part of the evolution, and it is different from the tau r relaxation time that we used here. In the L equals to 0, they are identical, but in general they are different. So, and the other quantities we can also estimate from the kinetic theory, other transport coefficients. So now we have a evolution equation for these extra degrees of freedom, and we can use it along with the conservation laws to solve these all the unknown quantities, and for the particular boost invariant system, one-dimensional boost invariant system, we solve this, and we obtain the temperature evolution of the medium. And this is how we found that this T ideal represents the case where there is no dissipation, the perfect hydrodynamics case, and we plot the ratio of this quantity. So these solid lines and dashed lines correspond to the different initial states, but the more interesting important point I would like to draw attention is the variation with the L. So as we increase the L, we find that the temperature becomes higher and higher. So what that means is when the temperature is higher, the system has more dissipation, more entropy is being produced. So we can directly correspond the higher values of L with the increase in the temperature or increase in the dissipation. So this will become important in a later slide that I will talk about. So next we wanted to let go of the chargeless case and consider the charge system. In that case, we also have to consider the number diffusion current, and that's how its evolution equation looks like. Now, this also has a relaxation time, the tau n, which is different from both tau r relaxation time and also the tau pi, the shear relaxation time. So RTA had this restriction that no matter what diffusion mode I'm working on, which viscosity I'm considering, this is always the same. It remains a tau r, but RTA is not does not have this restriction, and we can work with different relaxation time for different modes. So we wanted to plot these two ratio of the relaxation time. Just, I mean, out of curiosity, not that it will give us some great information. And I like this plot, although we do not understand what this represents, because this is surprising, because in the only part that we do understand is that L equals to 0 limit, where it converges towards 1. So in that case, it should become identical.
Samapan, so you have already finished 50 minutes. Maybe you can take 30 more minutes. So we'll ask only Arjun questions. So we will let him speak main part.
So, okay, then I will just probably skip and point out that the L equals to 1 value corresponds.
You explain everything.
Okay.
I'm just telling that you have 30 more minutes. So you try to finish the main part.
Okay.
You don't have to rush. I'm just asking the audience to keep the questions for the last.
Okay. So as I was saying that in the L equals to 0 limit, it becomes 1. That is what we expect. But why it becomes 1 in the such large values level, we don't understand. And the fact that these blue and red dots correspond to the hard sphere scattering, and this is lambda phi 4 interaction. Now, this is very interesting for us, that because if we look at this table, so in this article, they provided the results from the lambda phi 4 theory, and we find that most of the transport coefficients, they exactly match with the results from lambda phi 4 theory. So this really convinces us that if I want to capture some physics of the lambda phi 4 theory without going through the laborious calculations, I can do with this just L equals to 1 parameterization. So now I move on to some applications of these theories. For example, for one is studying properties of quarkonia, which is a bound state between quark and antiquark. So there is some binding energy of this bound state, the EB, and it depends on the temperature of the medium itself. So as the temperature becomes high, the binding energy is supposed to be lower. And now if we recall that higher values of L means higher temperature. So if I consider a theory which has large values of L, then the binding energy will be lower. And also, as my system evolves, it cools down, so the temperature will become low, and binding energy will be higher. So that's exactly what we found, that as the system expands in time, the temperature would cool down and the binding energies increase. And moreover, these as I increase the value of L, there is more dissipation, so higher temperature, and the binding energy will further decrease. No, this is just a study where, I mean, we compared various values of the L. It's
Number
yes,
two.
I agree. It's just a because we could plot, we did plot. Okay, so this idea of quasi-particle hydrodynamics that we were talking about. So here, the question that we ask is how much this parameterization itself is valid. We don't know. So in fact, this parameter L, we know that it depends on the particular theory of our system. So as the system evolves, it goes through different energy scales, and the interaction processes involved will differ. So in general, the L should also become a function of temperature itself. So we wanted to construct a theory where we could extract this kind of temperature dependence. So the particular value of the temperature dependence is not that important, but what is important is that the L does depend on temperature, and that's what we show. For this, we consider a Boltzmann equation of this kind, where we have this effective mass term, and we have to consider these bag terms to ensure the thermodynamics, all these things. So this is what we found, that if I try to, so there is this paper where the authors extracted the values of shear viscosity and bulk viscosity from the experiment. They compared with the experimental data, and this is what they extracted, and this blue line represents that. And we wanted to fit our theory for different values of L. And we found that if we want to fit the data, this is what the L would look like. So it does depend on the temperature. So, and in the process of doing this, we also found that if you recall, there was this earlier paper where they first proposed a modification of the collision kernel, which is called the novel RTA. So we found that our results and their results are exactly identical in this case, in general.
What is the value of L you choose for below TC?
So we don't, I mean, to match the data, we don't go below TC.
Or exactly near TC you have something.
Here, I mean, beyond this, so the point is that we see that there is a deviation, because it is QCD, as I mentioned, it should be between 0.0 and 0.5. Now, as I go lower in temperature, it deviates from the data. So that is a kind of indication that this parameterization itself fails. So in that region near TC, it is not correct to consider this kind of parameterization and try to fit the data. So if I could fit the data, then in that case, my L would have been negative. So, but that is weird.
Because this is this parameterization from perturbative QCD.
Yes.
Okay.
So now I come to the more interesting part, that is the spin hydrodynamics, where I spend most of the time in my research. So there is a observation in 2000. There is a prediction in 2004 of spin polarized hadrons being observed in the being produced in the heavy ion collisions, and it was observed in 2017 in this STAR experiment. This is the data of the global polarization as a function of the collision energy. Now, there has been some other possible observations as well, but this is the first observation, and it opened a new direction in our field. And there are recently various studies are being done in the spin polarization itself. So what this says is that the global polarization increases as I lower the collision energy. Now, this kind of behavior was explained by theories that assume my spin degrees of freedom are equilibrated. So what that means is that they assume that the spin degrees of freedom, they are controlled only by the thermal vorticity, nothing else. So if they do assume that, then the global polarization data is explained exactly. Okay, so this is a polarization. So there is this collision between the heavy ions, and there is in non-central collision, there is a global angular momentum. So the polarization along this direction is called the global polarization. Yes.
Total angular.
Sorry?
The total angular momentum, or what I'm like?
Yeah, the polarization along the direction of the total angular momentum.
Polarization of what?
I mean the particles. I mean, so
of the constituent particles.
yes, constituent particles.
Averaged.
Particularly lambda hyperons.
Averaged. Okay, never mind. We can talk about it.
It's lambda. I mean, you've got data for
This is for the parameter function.
Yes.
That's the spectator part. Generator and your chart. That's the
lambda has been a problem from the beginning. No, even in PP collisions, lambda is produced polarized, and there is no explanation as far as I know for that yet. So whether it is due to hydrodynamics or QGP, even at PP level, you are going to have polarized lambda. So that effect, I don't know if you have taken into consideration when you look at these systems.
No, I think this is particularly for this.
Because I mean, there is already a polarized lambda, right? Even in PP itself.
Okay.
I think it comes out with some 30% polarization, which is much larger than what you're seeing here. Okay, so I mean, I remember this from many years ago, but it's substantial. I don't know the PP conditions, lambda comes out. Yeah. Now he's talking about heavier. He's saying it is about 5 to 10%, right? So there's already a phenomenon which is not understood. This is over and above that. It is not polarized. No, not polarized. Unpolarized. Lambda is produced. Yes, yeah. In fact, tau is produced polarized. Lambda is produced polarized. It's not really understood.
Okay. But this global polarization in the context of heavy ion collision, they are understood. I mean, this is really dominated by the thermal vorticity of the system. So if I just proceed, there is another polarization in the experiments called the longitudinal polarization. This is observed along the beam direction. There is a transverse plane, and what it says is that it measures the average polarization of a particular as a function of the azimuthal angle. So the theory that was able to explain this polarization behavior completely contradicts the experimental observation. So here they say the first quadrant would be positive, second quadrant would be negative. The theory predicts that the first quadrant would be negative and the second quadrant would be positive. So this is based on the idea that polarization is controlled only by the thermal vorticity. So this was a big problem for us, our community, for a long time. And recently there was this proposal of shear polarization, shear induced polarization. So they claim to have solved the problem, but there are some subtleties there, because indeed, if I consider my spin polarization to be dominated by shear, it solves the problem. But if I consider my vorticity, if I put back the vorticity, then it again becomes very negligible. I mean, it cannot describe the data, and to describe the data, one has to make some assumptions that cannot be substantiated with the physics very well. So I would say the problem still remains. Yeah, order of magnitude.
P naught. If do I compare P naught value? I mean, what is it that you're plotting on the right hand side? P naught, is it?
Which plot?
What is on the x-axis? P naught and P1. Is it? What is it? I can't read it.
This is Py and Pz. I mean the azimuthal angle.
Okay, and what are these fit parameters? Cos theta, right? You're no left hand side plot.
Okay. So this is the mean polarization of a particular subsystem, and it depends on the azimuthal angle, the angle of in the transverse plane.
There is also the polarization, is it?
Yes. So the first
But
quadrant.
that's orders of magnitude smaller than the right hand side, right?
Yeah. So yes. So this does not explain the data. So that was the point. The point was that it not only fails to describe the data quantitatively, it also fails qualitatively. So our point was that this remains ambiguous, and we asked the question whether dissipation plays any role in the system. And for that, we wanted to formulate the dissipative spin hydrodynamics. For this, we start from the fact that now the system, the medium has some rotation. So in that case, we have to consider the conservation of angular momentum as well. So the total angular momentum can be split into the orbital part and spin part, and orbital part looks like this. Now, if my energy momentum tensor is symmetric, additionally, I have the spin part conserved separately. So that means there is no conversion of spin and orbital angular momentum. But there is one subtle issue that this splitting of orbital part and spin part, it is not unique. There can be other types of splitting as well, and this is known as pseudo gauge ambiguity in the community. And we found that the pseudo gauge ambiguity vanishes when we consider large distances as the system starts to behave like a classical system. Now, to construct kinetic theory, what we have to do is extend the phase space. Instead of the position and momentum, we also have to include the spin in the phase space. And because we have a new conservation law, we also have to introduce a new Lagrange multiplier associated with it, which we call the spin polarization tensor. So now our job comes back to that. We want to determine the out of equilibrium part of the distribution function. So as a starting point, when this work was done, there was no modified collision kernels. We did with relaxation time approximation, and this is what we obtained. So the key takeaway points here is that the out of equilibrium behavior of the fluid variables, the number current and the energy momentum tensor, they remain unaffected by the spin degrees of freedom. But the spin degrees of this was the first work where we calculated this correction to the spin degrees of freedom. And we found that it not only depends on the spin polarization, but also some other hydrodynamic variables gradients as well. So this was one of the first studies where we found that spin polarization is probably related to quantities like shear viscosity, shear stress tensor as well. This one. So okay, so this is just a contribution of spin tensor from this coming from the scalar expansion as fluid expands. This is for the any diffusion in the particle diffusion. This is for the shear stress tensor, any polarization occurring from the shear, and this is the what we call spin diffusion. So there is no any particular strongly motivated naming, but this is something we call the spin diffusion.
And the bulk part comes from the first term.
This one, yes.
That depends only on theta.
Mm-hmm.
Why is it so?
No, I mean because it is there is a tensor structure with appearing with theta. We call it bulk. That's why.
Where is the angular?
So angular momentum is conserved separately. So
we're only conserving the total L plus S.
mhm.
So S fluctuates. Are you saying the fluctuation in L is exactly the opposite of S? Are you putting that condition or not?
No, we don't really work with the angular momentum part. Yeah.
You formulate it?
Yes, I understand. I mean, there should be some part as well, but we forget that part. I mean, it exists, but I mean, okay. So when we're trying to measure the polarization of the particles, then it is found that the orbital part does not play any role in the polarization's value. Only the spin part would.
No, that I understand, but the observation. The formalism. You N and T also don't matter for that. Yet you are representing them. Why not L also? Be complete.
So I mean, L part is because L is rated like this, right? So if I know energy momentum tensor, L is automatically known.
No, it's a different movement.
Mhm.
It's a different movement that you're looking at. In terms of your Fs, it's a different movement that you're looking at.
Mhm.
Now, in the phenomenon or parameterization that you have done, the fluctuation S, how does it match with fluctuation L? That could be just for self-consistency, one would like to know whether they are correlated. They should be. But what is it? One should be honest about what was spelling out.
Yeah, I don't think I can say anything about that. Yeah, that's.
It has an X mu component as well. Yeah. Yeah.
Now you're putting an X on.
Yeah. That's important. Yeah. Yeah.
Okay, so there is one more thing that we want to add that is the magnetic field, and we did that. So when there is magnetic field and rotation involved, there are two complementary effects: the Einstein-Diaz and Barnett effects, where if I put my magnetizable material in the magnetic field, it starts to rotate. And if I rotate my magnetizable material, it can generate a magnetic field. So these are two opposite phenomena, and this is what we observe when we introduce magnetic field as well. And in this case, the energy momentum tensor and angular momentum of the fluid part only, they are no longer conserved. They are given by some force and torques of the system. And So we can again solve the Boltzmann equation and do all the distribution, solve the distribution function and obtain the transport coefficients. So one of the interesting thing here is that I have only given the number currents correction here. And now you can see that it not only depends on the diffusion of chemical potential, but all other possible gradients. So it connects with the thermal vorticity, and this is because these coefficients now include magnetic field and spin as well. So this is one example where the spin can give a feedback to the fluid itself. So and then we wondered whether these theories that we are considering, whether they are actually explaining the actual data, and we sorry. Yeah, I mean, this is just one equation because I could not give the more details. So this is the total angular momentum is now not conserved, but the spin is still conserved.
That is still.
Yeah. So we plotted the mean polarization in the longitudinal direction, and we found that to ensure that that it matches with the data, there has to be some finite dissipation in the spin degrees of freedom. And the spin relaxation time turns out to be of this order, which matches with some other earlier works. And so this is significantly larger than the usual relaxation times for other hydrodynamic cases, which is about 1 Fermi over C. So this inspired me to consider the case where relaxation time of spin, the relaxation time depending on the spin itself. So for that, we go back to the fact that RTA, as before, will not be able to follow this work, and I used ERTA, and this kind of parameterization is used. Now here, as you mentioned, the L2 parameter here, it's this is again just a parameterization, but L2 here cannot be used as a fractional value. It can only be integer, because again there is a problem with solving the integrals itself. So we solved these equations, and because ERTA could work in a general frame, so we obtained the frame invariant transport coefficients. And this is the work where we first have the expression of the spin transport without any frame dependence. But this is not sufficient, because all these theory that we have been discussing so far are first order theories of spin, and first order theory is known to be acausal. So what they do in literature is go to second order theory, but the issue there in second order theory is that it introduces many non-hydrodynamical degrees of freedoms, which do not really have any physical significance from thermodynamics. So there were these group of people who proposed a first order causal theory which uses only thermodynamic variables, and I would like to formulate that theory for spin hydrodynamics as well. Now
Hi,
here
one
comes
question, one quick question. Can you go to the last plot just 2 slides ago? Yes. So you are saying that your tau s is, so you are going for a different parameterization. Why with the L2? Because you think that this does not address the data properly, or?
Oh, no, this is not with the L2. This is this work, but this is done with the RT where there is no L2 parameter.
Yeah. And what is the reason for going for the different parameterization and where L2 has to be integer, as you said?
So the integer part is because unless it is integer, we cannot solve the integration. I mean, we cannot perform the integrations. That's the just point. And this is because this parameterization is taken because I just wanted to work out an example where relaxation time can depend on spin. So this is just an exercise. I mean, it's not that this is the only possible choice.
Okay. Does the data suggest that you need to have, I mean, is it something that you just wanted to make the theory complete, or it is something that has to do with the data that you are not able to explain it with the first parameterization and you are going for the extension?
Yeah, so the motivation was this kind of plot where we found that the spin relaxation time is important, which is different from the relaxation time for other degrees of freedom. So I wondered whether whether this kind of behavior tells us that this relaxation time should depend on spin as well. That's why I wanted to construct this.
Okay, I understand.
Okay, so
Thanks.
Okay, so now ERTA has limitation here because ERTA ensures the conservation laws in an order by order manner, and in that case we cannot formulate this kind of first order causal theory. So the way out is to go for this novel RTA, but it was available only for spinless particles, so I had to extend it to particles with spin, and this part is the only RTA solution, RTA collision kernel, and these two parts were introduced by these people. The rest of the terms are for spin. So I obtained this collision kernel, and then I solved it and obtained the transport coefficient. So I'm not going to details about that anymore. So because the results up to first order is exactly same as ERTA. So now spin. So whatever I've been talking about is what is called classical spin. It is obtained from the semi-classical approximation of the theory, but spin itself emerges from quantum field theories. So, and the connection between QFT and kinetic theory is obtained by the Wigner function. So we wanted to study the Wigner function itself. For fermionic fields, one can decompose the Wigner function into using the Clifford algebra. So we wanted to solve the Wigner function for particular systems. So as an example, we considered the Angel model, the Lagrangian, and this is the corresponding equation. Now, because we know how the Wigner function is defined, we can obtain the kinetic equation for the Wigner function as well. So we want to solve this equation, but the general solution is very difficult to obtain. So we consider some specific cases. The first case is when we have the pi field 0 and the sigma is given by some time dependent parameter which has a mass dimension, so we call it effective mass. So we found that in the boost infinite case, the spin density decouples with the mass part m of t, and there is not much interesting thing going on. But in the non-boost invariant, when we break the boost invariance case, then we find the spin density is given by this, where the mass comes in the denominator. So what this indicates is there is a situation where my system is going towards a chiral limit, then my polarization blows up. So this establishes first observation that maybe there is a correlation between spin polarization and the phase transition. And it was later another proposal that they substantiated this. Now, there is while searching for the literature, we also came across the one particular case where they can solve this equation exactly. They can obtain the wave functions exactly, and this is when the sigma and pi field has a inhomogeneity in space, and they vary as a sinusoidally. Here, m is the constant. So, in this particular case, we can have an exact solution of the wave function. And more interestingly, if I try to obtain the energy of for energy eigenvalues, then the energy eigenvalues are now split. So if this r equals to 1 and 2 correspond to spin up or spin down, and because of this inhomogeneity factor, we have this splitting. So this is what the energy splitting would look like. So this result was known for a long time, but what we was surprised to see that there was no interpretation that this r equals because of this kind of splitting, the system's natural tendency would be to populate the r equals to 2 phase only. So this kind of gives a naturally gives rise to a spin polarization. So this can be the inhomogeneity can be a source of spin polarization as well. So that's what we wanted to see, and this A3 is the axial part of the axial part, and it corresponds to spin polarization directly. So when this inhomogeneity goes to 0, axial part goes to 0, and there is no spin polarization. But when we have finite inhomogeneity factor, there the spin polarization increases. So this is one interesting observation, but there is another even more interesting thing is that now we find that Wiener function has been solved exactly. So this is actually a non-perturbative result. We don't need to do any expansion here. But and in that case, this is the one of the kinetic equations for the Wigner functions components. And if we expected that if we do a semi-classical expansion at this stage and consider only the leading order term, then the equation should be valid. So I also considered the leading order contribution from the solution, and this should valid. This should match. So up to leading order, this is the solution, this equation. But surprisingly, that the exact solution does not follow this relation. So what we learned from here is that in this particular case, semi-classical expansion cannot be completely relied on. So we found an example where we're not saying that semi-classical expansion is invalid. It has no use, but our message was that one has to be careful when we are considering a semi-classical expansion, that it may fail in certain cases. So now, because of this, we've found that semi-classical description of spin can be unsatisfactory often, but an exact quantum theory is very restrictive. It has some constraints. So the original work that started all this.
Because there are inhomogeneities as well in your system. Is that the take-home message that you're giving?
Yeah, I mean,
because if there were no inhomogeneities, it would have been.
Yes. Okay. So the point was that for particular cases, it can be.
I know.
Yes.
We do expect if an inhomogeneity is present, there can be other terms apart from this standard expansion.
Yes.
That's
okay. So the original work that started all the spin hydrodynamics, they calculated the mean polarization of spin-up particles, and they found this kind of expression. Now the issue with this kind of expression is that this B star and E star, they are the star here represents the particle rest frame quantities, and B and E are the electric-like and magnetic field components of the spin polarization tensor. So what the issue with this kind of expression is that it is no longer bounded. So it can acquire a large value, but so that's why if I have a finite system, my polarization should be finite. But this kind of expression violates that expectation. So we knew this was an issue, and that's why people worked on cases where both E and B are small, which results in the small polarization limit. That's why whatever work we have been doing was in the small polarization limit. So we have been wondering about how to improve this situation. We found that the source of this problem was the particular distribution that was proposed in this article back in 2013. So we came up with a new proposal. So and this what we found is that even though we cannot ensure all this, that the macroscopic degrees of freedom, we cannot perform the integrals exactly up to all ordered in omega, but we can ensure the thermodynamics is satisfied. So we found that this kind of solution expression holds irrespective of whether it is small polarization or very large polarization. This was not, one could not do this before with the semi-classical expansion or this kind of distribution function. So another thing we found that this is the second law of thermodynamics, where this is the entropy production, and we found that when everything is in equilibrium, everything is conserved, there is no generation of entropy, and but in cases where the spin current is not conserved, that is when there can be some transfer of angular momentum between spin part and orbital part, this will be not conserved and my entropy will be produced. So what it means that the transfer of spin or transfer of angular momentum is a purely dissipative phenomena. And the other thing is that this equilibrium distribution turned out to be non-linearly causal and stable only in the equilibrium part. So these are some summaries. Maybe I will skip this and go to the future plans. So in the near future, I would like to first continue with this particular work that I have been doing right now, is the formulation of causal first order spin hydrodynamics theory. The importance of this work is that the phenomenology of spin hydrodynamics and any other theory that uses hydrocodes is based on second order theory. And as I mentioned, the second order theory consists of variables that do not really have any thermodynamic origin, and they're very difficult to interpret. So I would like to solve first order causal theory where everything is thermodynamic, and then I believe that the numerical solution can be done easily. The next problem is the formulation of spin hydrodynamics for spin 1 particles. So apart from the global polarization and longitudinal polarization that I explained, these are for lambda hyperons. There is also observation of vector meson spin alignment, and that is also remaining unexplained. So the theory underpredicts the experimental observation by a lot. So this is not still explained. There has been many attempts. So whether dissipation plays a role there or not needs to be seen, and for that we would like to formulate the spin hydrodynamics. And another thing is that the development of a spin hydrodynamics with fluctuation. Now, why this becomes important is that we had a hint earlier that phase transition and spin polarization may be related to each other. So near phase transition, the system fluctuates widely, and in that case the gradients can become as large as the fields themselves. So that's why traditional hydrodynamics cannot handle those kind of situations. So there has been some formulation of hydrodynamics with fluctuation in other contexts, but we want to extend that to spin hydrodynamics as well. So these are the near future plans, but I have some long-term plans as well, which I've become interested, but I have never worked on these things. So I just had some problems in mind, and I found that these probably can give us the solution. The first problem is that formulation of relativistic hydrodynamics using renormalization group approach. I became interested in this work because, as I mentioned here, that uh, hydrodynamics depends on a gradient series expansion, and whether we can formulate hydrodynamics or not depends whether that the value of the gradients. If the gradient is small, then it's okay, we can do this expansion. But if the gradient itself becomes large, then the series expansion comes into question. And to avoid that, it will be very nice if we can have a non-perturbative theory for hydrodynamics as well. For that, I wanted to use the FRG approach. And the next is the Schwinger-Keldysh formalism. So this stems from the question that how does dissipation arise in from QFT to hydrodynamics? So if I consider even in interacting field theory like lambda 5/4, there is this would give rise to a ideal situation. There is no dissipation there, right? The laws are conserved there. So dissipation would mean I have to introduce some temperature, and that's why I have to go to thermal field theory. And furthermore, it will be an out of equilibrium system. So we have to consider a real-time formalism, and that's why Schwinger-Keldysh formalism would be appropriate to describe that kind of system. So I think maybe this can be one of the direction that one should go. And lastly, there is a problem in heavy ion collision that we don't understand, that the medium becomes thermalized very fast, like within maybe 1 Fermi over C or so, the medium becomes thermalized. So there is a problem of fast thermalization. We don't understand why this happens. So I was trying to look for answers how thermalizations occur, and I found that quantum information theory has done some work here, and mostly this called eigenstate thermalization hypothesis. So they use that uh, to, and the eigenstate thermalization hypothesis is connected to this quantum entanglement and quantum complexity. That's why I want to use this as an example. So what eigenstate thermalization hypothesis states is that if I have a simple operator to start with, which is local, with time it will evolve. Even if it's isolated system, it will evolve, and the operator will become non-local, large, so large that it effectively forms a bath. And that's how probably this thermalization comes there. So there is some indication how one can go from non-thermal system to thermal systems there. And quantum complexity is a measure of how this process goes on. So that's why I wanted to work on this. But yeah, I'm not sure whether these works are feasible or not, but I have to go through. So it's like in the next 2 or 3 years, I'm to go through these studies, and I want to understand whether these are possible or not. Now, there are some other warm-up projects that I'm planning to do, these are some simple studies which maybe some I can do it with some students, like uh, formulation of spin hydrodynamics with maximum entropy principle. So there was one work with by Chandrodaya Chattopadhyay. He formulated the entropy maximized distribution for massless chargeless case without any spin. So I would like to generalize this. So these works will be like giving warm up project, like to become familiar with how the theory is being solved in hydrodynamics. And the other work is that the spin polarization from the Angel model that we saw, it was done for a static system, but maybe we can generalize it to rotating system and also include the magnetic field as well. So that would be some interesting problem. So these are some publication listed. So I have not gone through all of the works here. So that's
Okay, let's thank Samapan. If you have any questions, you can ask.
You described lambda polarization using the classical spin model, but these are all fermions. So why is it working so well? And you can explain the data, because really this theory should.
yeah. So the lambda polarization that we observe is in heavy ion collision is very small, and what classical theory of spin also tells us that it can be worked out only in the case when the polarization is small. So I believe that's why it can probably give some predictions.
And this polarization that we were seeing, this is at kinetic freeze out, right?
Yes, in the experiment, that's yes.
So how do you convert your hydrodynamic picture to?
So we have to go through this Cooper-Frye.
And how does this Cooper-Frye modify when you have spin?
Okay, so there is some ambiguity involved here. So there are different groups working on these topics. So the exact prescription for Cooper-Frye for cases with spin is not settled. So there are different groups who give different prescription.
But
So,
then how much error band will you have when you compare with the data? Your theory predictions, including the Cooper-Frye, because all these data you're plotting at kinetic freeze out. So you should give a error band in your theory predictions also. So how much is that band?
okay, so no, that I have not.
Maybe it will be interesting to look at that band. Yeah. And secondly, in the thermalization case, usually we understand the thermalization first occurs for the non-perturbatively interacting modes, because the modes which strongly interact, they first thermalize, and then of course the perturbative modes then follow. That's the picture we see from our studies. So now here, if you want to do formulation of hydrodynamics, so when you're talking about this long wavelength modes, do you mean those non-perturbative modes you're describing using this whatever formalism you want to generalize, or how are you planning to do for the generalization of your hydrodynamic formalism using quantum entanglement?
No, so that is probably will be so the non-perturbative part that will be probably done with this FRG approach. So there, I think.
No, the non-perturbative part, even at high temperatures, where your quasi-particles are gluons, they can be also interacting non-perturbatively. The magnetic sector of the means everything is not perturbative even if you go to high temperatures. Even if you go to asymptotically high temperatures, the magnetic part or the low momentum gluons are always non-perturbative. If you look at the spatial string tension, it is always rising linearly.
Yeah, but I'm not.
So why do you want to do FRG? Means those non-perturbative features can be done because these are non-perturbatively interacting gluons. FRG is a theory of your baryon and meson loops are included in the propagators.
Okay, so my motivation was that the cases where the gradients themselves become very large. So in that case, the series expansion will fail, right? So it would be better if I don't have to go through this series expansion and I get the non-perturbative result directly. Then I can.
So you want to start with hadronic theory and then do FRG to get the low or the long wavelength limit of that.
Okay. So So maybe there is one can go through that way, but what I had in mind is that there are some Lagrangian formulation for hydrodynamics itself. So I want to use those Lagrangians and then do the FRG without. I don't want to go through these Masons or.
Any online participant? You have any questions? No. If you don't have any questions, like, let's thank again. Thank you.